Hello everyone, I'm Ye Hongjie from Institute of Software, Chinese Academy of Science. Today I will introduce our paper entitled Knowledge-Based Environment Dependency Inference for Python Programs. Python is one of the most popular programming languages, and it is widely used in many application fields. Python has achieved an active ecosystem. PyPI is the second most fast-growing package repository. It holds over 300,000 packages and increases an average of about 200 new packages per day. Thus, people usually use Python code to improve development efficiency. For example, someone wants to find all tomcats in a movie, and he searches Stack Overflow and GIST for reusable code snaps. He gets a code snap demo superglue, but the source code is provided without its dependencies. Finally, he runs the source code, but encounters syntax error and import error. It seems easy to run a program containing a reused code snap. User can first install a compatible version of Python interpreter and install all the dependent Python third-party packages. After that, user can run the program. However, inferring dependencies for Python programs is not trivial. Take the following code snap demo superglue as an example. Firstly, demo superglue imports pathlib in line 1. Pathlib is a standard module, and all standard modules are contained in the Python interpreter. Pathlib is contained in the Python 3.5 or above, which illustrates the compatible version of the Python interpreter. Secondly, demo superglue imports matplotlib in line 2, and matplotlib is a third-party module contained in the third-party package matplotlib. And in line 3, demo superglue imports cv2, another third-party module contained in OpenCV-Python. We can find that module names are not always consistent with the package names. Thirdly, OpenCV-Python depends on a system library, libopencv-contrib. We should install it before using the package. Lastly, a package can be required by others at the same time with different version constraints. Therefore, users should carefully choose a proper package version to avoid potential version constraint violations. Dockerize.me, pip request, and snifferdog are three most related work for inferring dependencies for Python programs. They mainly focus on dependencies of Python third-party packages. However, they pay no attention to the Python interpreter and pay little attention to system libraries. Moreover, none of them consider the interrelations among the dependencies. As comprehensive knowledge is required for constructing a compatible environment for Python programs, we are motivated to propose a knowledge-based approach to infer dependencies for Python programs. First, we collect and extract domain knowledge from multiple data sources, and construct a knowledge graph PYKG, which can portray the relations among the third-party packages, the Python interpreter, and the system libraries. Then we propose a knowledge-based environment dependency inference technique, PyEagle. Given a target Python program, PyEagle first extracts its features, and then infer dependencies of the three types for the program, with the support of constructed knowledge base. Let's begin with the knowledge graph model design. The three types of dependencies, packages, libraries, and the interpreter are considered as the basic elements of the graph model. Python interpreters support syntax features and contain multiple standard modules. Third-party packages are identified by their contained third-party modules. Red edges between nodes describe the relations between features and the dependency resources. Meanwhile, the knowledge graph records dependencies between packages and libraries. It also portrays the dependencies among packages and compatibilities between the interpreter and packages. Blue edges are interrelations among dependency resources. Based on the knowledge graph model, we organize knowledge collected and extracted from multiple sources. We obtain the knowledge of what syntax features are supported by each Python version. To this end, we summarize context-free syntax features of Python versions and transform them into regular expressions. For example, positionally only parameters is such a syntax feature, and we convert it into a regular expression. The obtained regular expressions are further used for identifying the compatible Python versions. Then, we collect the knowledge of what modules are contained in each Python interpreter and third-party packages. We analyze the directory structure to extract modules in different levels. Python files are modules, and folders containing init files are also modules. For example, CV2 is a top-level module contained in OpenCV-Python, and CV2.version is a second-level module. After that, we analyze metadata files of a third-party package for obtaining the compatibility between the package and the Python interpreters. For example, OpenCV-Python requires Python not lower than 3.6. Thus, it is compatible with Python 3.6 and 3.9. We also analyze the metadata for obtaining the dependencies between third-party packages. For example, OpenCV-Python requires NumPy not lower than 1.19. Thus, it depends on NumPy 1.19.3. Dependencies between system libraries and Python third-party packages are not documented. To obtain more comprehensive knowledge of what system libraries are required by a certain package, we propose a similarity-based mining method in addition to the association rule mining method proposed by Dockerized.me. We notice that some pip installable third-party packages have similar apt installable distributions with slight difference in their names and structures. And the system-level dependencies of apt installable distributions can be obtained through executing the apt commands. Thus, if an apt installable package depends on a set of system libraries, it is highly likely that the similar pip installable one depends on those system libraries too. Finally, we analyze over 10,000 of third-party packages and 6 versions of the Python interpreter and construct a knowledge graph containing hundreds of thousands of entities and millions of relations. In stage 2, we propose an approach to infer dependencies for Python programs. Given a target Python program, PyEagle first extracts its features, and then it queries the knowledge graph with the features to get a dependency candidate. It infers dependencies of the 3 types for the program through constraint solving. To extract features of the program, we first pass each Python file into AST and then identify modules from import nodes. For example, by analyzing line 1, we can find that the code snap imports a top-level module, pathlib, and a second-level module, pathlib.path. Then we query PYKG and classify modules into standard modules, third-party modules, and local modules. For example, pathlib is a standard module, and CV2 is a third-party module. Finally, we take standard modules and third-party modules as module features. On the other hand, we extract syntax features by matching the program code against syntax feature in the form of regular expressions. For example, PyEagle identifies that the code snap uses a syntax feature fstring. Then we query PYKG for dependency candidates. we query candidates' Python versions with standard modules and syntax features. For example, we found Python 3.6 and 3.9 both contain the standard modules pathlib and pathlib.path, and they both support the syntax feature fstring. We query candidate packages with third-party modules. OpenCV Python 3.1 and 4.4 contain the third-party module CV2. Matplotlib 2.2 and 3.3 both contain third-party modules matplotlib and matplotlib.cm. Then, we get the transitive dependent package and system libraries. Matplotlib depends on pytz and pylo. OpenCV Python depends on NumPy, and it depends on a system library, libopencv contrib. Finally, candidates from a target program-centric subgraph. Nodes in a subgraph are versions of dependency candidates, and edges are interrelations among them. This slide presents a part of the subgraph of the example code snap. Then we determine versions of candidates while constraint solving. To avoid dependency conflict, we propose 3 constraints. The first one, existent constraint, means the Python interpreter and direct dependent package are necessary and must be installed. For example, OpenCV Python is a direct dependency, and we must install a proper version. The second one, unique constraint, means at most one version of each resource can be installed. For example, one can install Matplotlib 2.2 or 3.3, but cannot install both at the same time. And the last one, version constraint, means each installed package version should be compatible with any others depending on it. For example, one cannot install Python 3.6 and Matplotlib 3.3 at the same time because they are incompatible with each other. And to achieve the best solution, we propose 2 requirements. The first one is install packages with versions as new as possible. For example, if Matplotlib 2.2 and 3.3 are both OK, Matplotlib 3.3 is preferred. And the second one is install packages as few as possible. For example, if Matplotlib 3.3 is selected, pytz is not necessary. To this end, PyEagle solves the constraint with optimization objective. After constraint solving, the final solution contains proper versions of the package, the libraries, and the Python interpreter need to be installed. To evaluate the effectiveness and efficiency of PyEagle, we propose the following 3 research questions. How effective is PyEagle in inferring dependencies for Python programs? How efficient is PyEagle in inferring dependencies for Python programs? And how does PyEagle perform compared to the other works? We evaluate PyEagle on 3 datasets, HG, SD, and JPD. HG is the dataset used in the previous work Dockerize Me, and JPD contains Jupyter notebooks listed by SnifferDoc. To evaluate whether our approach can be used in more complex scenarios, we collect 100 Python projects from GitHub and create an extra dataset, SD. Projects in SD are executable, explicit, and diverse. Here is the experimental result. Our work, PyEagle, reaches 46%, 62%, and 60% accuracy on the 3 datasets respectively. As for execution time, PyEagle reaches 0.7, 2.5, and 2.9 seconds per project on the 3 datasets. PyEagle failed to infer dependencies for all the programs because of missing dependencies, incompatible dependencies, incompatible operating system, and conditional dependency. This is an example of missing extra dependencies. XLRD is an extra dependency of Beautiful Soup 4 and will not be installed automatically. As a result, the CodeSnap encountered runtime failure because of missing XLRD. And this is an example of conditional dependency. The program conditionally declares its dependencies on standard modules specific to Python 2 and Python 3 in a try-catch block. It does not consider the context of import statements and cannot find a Python version containing both modules. As for research question 3, we compare our work with pip request and Dockerize me. We do not compare it with Snifferdog because its repository do not offer the critical component API bank. Comparing to pip request and Dockerize me, PyEagle reaches the highest accuracy on the 3 datasets and infers the least third-party packages. However, PyEagle infers more system libraries because the obtained dependencies between system libraries and Python packages may be false positive. As for execution time, PyEagle runs faster than Dockerize me. Because we cache a part of knowledge graph in memory, PyEagle runs faster than pip request in general because we store knowledge locally, while pip requests need to query PyPI for versions of packages. PyEagle runs little slower than pip request on the whole SD because pip request exists immediately when encountering syntax error during feature extraction. But PyEagle tries changing the Python interpreter version and extracts its features again. In conclusion, we propose a knowledge-based approach to infer dependencies and generate runtime environments for Python programs. The approach contains 2 stages: knowledge graph construction and runtime environment generation. The experimental result shows that our work is more effective and efficient than the state-of-the-art work. Our work is available on GitHub. That's all. Thank you.